Hey guys, hope you're all doing good and welcome to a new video. Today we will be learning how to perform cavitation based simulations using Converge CFD, and for this we have picked up an interesting problem. So what you're looking at on the screen is what people call as the Winkelhofer nozzle. So this geometry is based upon a study that was actually done by a lot of people, and in this particular case we are going to be looking at the one that was done by Argonne National Lab. Right, so the paper is titled Exploration of Cavitation Induced Erosion Metrics in Throttle Flow Simulations. So the primary reason for this particular group to work on this study is to look at the effect of cavitation on fuel injectors. So the idea is very simple, and most of you might know what cavitation is. So here, for example, you can see that there is a nozzle and there is abrupt size and there is abrupt change in flow radius. So for example, here the flow diameter is this big and suddenly the flow diameter is reduced by having a throat. This causes a huge low pressure region or an area of separation, correct? And when pressure becomes low, and if it becomes lower than the vapor pressure of the fluid, then what happens is the fluid instantaneously vaporizes into gas phase. So this affects the injector properties in terms of delivering the required fuel flow rate, and this can subsequently affect the combustion performance and also the emission performance. And that is why in automotive applications looking at cavitation is very important. Now if you take in applications in the HVAC world or the turbo machinery world, cavitation is extremely important in rotating devices. For example, if you take centrifugal pumps, due to the high impeller speed, the pressure can actually go really low on the back side of the impeller tip, where low pressure zones can be created, and it is at these zones where the fluid that is basically being pumped can vaporize into gas phase, and it can form gas bubbles which can hit the structure and can cause corrosion and eventually failure of that particular component. So studying cavitation is extremely important, and computational fluid dynamics is one of the major tools out there that helps you study this complex process. So in Converge and many other tools, cavitation is basically studied using something called as a volume of fluid approach. Volume of fluid approach is basically a subset of multi-phase flow simulations. So in this particular case, since we have both liquid and gas phase, we call this as a multi-phase flow problem, and in order to run such a simulation we will be using the volume of fluid methodology. Now in Converge CFD, the transition from liquid phase to gas phase is described by this particular rate law. So dx by dt basically tells you the rate at which the liquid is going to get converted to vapor, and you can see that it happens based upon a time scale which is called as theta. Now theta is calculated based upon an empirical model, basically a model that has been created from experiments, where you have some key constants which basically helps you get the correct vaporization rate. Now these are the set of constants that we will be using for our Converge case setup. Now what I will be doing is I will be directly going over the case setup. Now this case setup will be shared with you, so you don't have to worry about setting it up from scratch. I will be going over this case setup from top to bottom so that you understand every step. So first of all, if you look at the model, you can see that it's really small. When you enable the bounding box, you can see that the largest dimension is just 2 millimeters. That's because we are looking at a nozzle and the nozzle size is extremely small. So the size of this nozzle is comparable with most diesel injectors out there. So if you look at the material properties, we are performing a gas and a liquid simulation together. So that suggests that this is a multi-phase flow simulation. Alright, so now let's look at liquid simulation. So here you can see that several liquid properties are being used, but the one that we really care about is C14H30, and that is what we are going to be using, which is nothing but tetradecane. And if you click on species, you can see that there's something called as liquid, and this is where we are telling that out of all those liquid properties that we had selected, IC14H30 is what we are going to be using. As far as the gas species, you can click on reaction mechanism to learn which are the gas species that are being used. Here we are using gas phase tetradecane and N2, which is nitrogen. So the reason why we are picking up gas phase tetradecane and liquid phase tetradecane is to basically enable the cavitation model, right? Initially you have liquid tetradecane in your domain, and when cavitation takes place, this liquid is going to get converted to vapor, and when it converts to vapor phase, it's going to be called as C14H30, but it is in the gas phase. And in order for you to run the simulation in Converge, you have to explicitly say which is your liquid phase and which is your gas phase. So that is done. If you look at the run parameters, it is a transient simulation. And if you look at simulation time parameters, you're running it for only 2 milliseconds, right? That's typically how long an injection duration is. But if you look at the time step, look at this. We are being extremely conservative. You know, our minimum time step is 1e minus 10 and max time step is 0.01. The main difference here, however, is in your CFL number. Typically, for the simulations that we have done so far, our CFL number has been 1.0, but here we are limiting it to 0.5. That means your velocity information cannot propagate more than one computational cell. In fact, it can propagate at a max only half of a single computational cell. That's basically what the CFL number is. And if you look at the other CFL numbers, that has not been changed a lot. And when you run the simulation, you will see that your CFL, convection based CFL, is going to limit the problem. How am I guessing that? Well, I will be able to explain that when you look at the boundary conditions. Solver parameters, we don't change it. We use the default values. If you go to boundary, the primary difference comes at the inflow and outflow. If you look at the inflow boundary, we have IC14H30, which is the liquid tetradecane, but look at the pressure value, right? So this is a huge value of pressure, and if you're reading it correctly, it's 100 bar. So it's 100 followed by 5 zeros, right? So that's 100 bar. And if you look at the outflow boundary, it's 30 bar, right? So there is a difference of 70 bar. That's a huge pressure difference, and that's going to drive the velocity very high. And that is why we are concerned about the velocity based CFL number, also called as the convection based CFL number. Hope that makes sense. The top and bottom walls, which are the orange boundaries, right? They are going to be wall boundaries, right? So you don't worry about them. If you look at the side wall A and side wall B, they are type 2D. That suggests that this is a 2D simulation, and you can see that from the shape of the geometry, you know, you can clearly see that this is two-dimensional. That is, flow along X and Y are the only ones that matter. Along the Z axis, the flow does not change. Then finally, at the throat boundary, we are just creating a separate wall. And then finally, we are creating a separate boundary for the throat, and then we are assigning it the wall boundary condition. Now, you can see that there is a cylinder type structure here. What is that? Well, we'll look at that shortly. Next comes regions and initialization. Now here what we are basically doing is we are creating a nozzle region and we are initializing that with 100 bar pressure, right? And you can see that I'm filling that with tetradecane and also a very small percentage of N2. This is basically done to help convergence. Even if you don't have it, it's fine. You can just have pure liquid tetradecane occupy this entire space. That's fine. But having a little bit of gas phase helps out with convergence. So let's click on OK here. For turbulence modeling, you will see that we are just using RNGK epsilon. Again, in this particular case, we are interested in cavitation, which is going to be an effect of pressure, and it's not going to be an effect of shear, right? So for that, the turbulence model should not be a huge issue, so we are not going to change it. The most important piece here is the volume of fluid method. You can see that there are a couple of techniques. Here we are just using basic VOF. The idea is we are going to be solving one transport equation for the liquid phase and one transport equation for the gas phase, and automatically the interface between the liquid and the gas is going to get calculated. We are going to be using the cavitation model. Here the liquid species is selected, gas species is selected, and you can see that it's a list that you get automatically, so make sure that you select it correctly. And then you basically set up your time scale coefficient, which we got from the paper. All of this is done, and let's click on OK. So then when it comes to base grid, you can see that the initial base grid is very small. It's 4e minus 5. Okay, and then on top of that you have adaptive mesh refinement. Now notice that we have adaptive mesh refinement based on two parameters, velocity and species, right? So we are doing it based on species. It's a permanent type AMR, and the AMR SGS is 0.0001. This particular value does not have a unit. So here what we are basically saying is when vaporization takes place or when cavitation takes place, you will have gas phase species and liquid phase species, correct? So we are just going to be tracking the curvature of the gas phase species in our entire domain. Wherever the value of the curvature exceeds 1e minus 4, we are going to be refining the mesh. Okay, and the maximum embed level is 3. So this is one set of refinement. The other set of refinement is purely based on velocity, which is completely on right from the start, and the SGS criteria or the subgrid scale criterion for that is 0.1 meter per second. So that's basically it. And when it comes to post variable selections, we are using pretty much all the values. In addition to the usual values, we are selecting void fraction. That helps us identify our gas phase and liquid phase correctly. Finally, when you look at output files, here you can see that the text output is written every time step. 3D output is written every 5e minus 5. So I think that's basically every couple of time steps you are writing an output file. The reason why we are doing that is to basically understand how the cavitation bubble starts to form. Alright, so with that, I would like to conclude this video. We are going to be running the simulation, and once we have the results, we will come back and we'll discuss that in another video. Thank you so much. I'll see you in the next one. Bye.